It's the last unit.
See, but that means we have to go to diploma soon, which is going to be hard. So, wait, when's our diploma?
It'll be in June at the end, towards the end of June.
Towards the end?
Towards the end. The
Like 20th-ish?
I'd have to look it up, and I can.
Waiting over 3 years for this. No.
That information's already out there, so I can look it up. Okay, yeah, so this is the last unit covering chapters 9, 10, and 11. Chapter 9, we're going to look at rational functions. So we'll graph and analyze, compare rational functions using transformations and technology, and we'll look at the behavior of graphs of rational functions near the non-permissive values. So a rational function is a function that can be written in the form f at x equals p at x over q at x. So basically you need a numerator and a denominator, and there has to be a polynomial somewhere. Okay, so one of them has to be a polynomial function. So some examples are y equals 20 over x, or c at n equals 100 plus 2n all over n, or f at x equals 3x squared plus 4 all over x minus 5. So got to have a numerator and denominator, and there has to be a polynomial somewhere. That gives us a rational function. So the rational function that relates speed to time for a given distance is related to the base function y equals 1 over x by a vertical stretch. The graph of a rational function in the form y equals a over x represents a vertical stretch by a factor of a of the graph y equals 1 over x, because y equals a over x can be written as a times 1 over x. Graphs of rational functions of this form have two separate branches that approach asymptotes at x equals 0 and y equals 0. So let's look at the graph of y equals 1 over x. We'll do this by creating a table of values, and we'll identify some characteristics of the graph. So first thing you should recognize is that x equals 0 is a non-permissive value, an MPV, a non-permissive value, because we can't divide by 0. So that is a restriction on the values that we choose for x. So we can set up a table of values that show values on both sides of 0, on both sides of x equals 0. For example, if we start with answer or values of x like 10, 5, 2, 1, 1/2, and let's say 1/4. So we're getting closer and closer to 0 from the right. When x is 10, y will be 1 over 10. When x is 5, y will be 1 over 5, and then 1 over 2, and then 1. But when x is a half, dividing by a half is the same as multiplying by the reciprocal, 2 over 1. And dividing by a quarter is the same as multiplying by the reciprocal, 4 over 1. So we can start to draw the graph of this. Again, we said that x equals 0, which is the y-axis, is a vertical asymptote. The other thing we can say here is that y can never equal 0 either, okay? Because 1 divided by a number is always going to give you some value, never 0. The only way a rational function equals 0 is if the top equals 0. 0 divided by something gives you 0. But the top is a constant, it's positive 1. Okay, so we say that x equals 0 is a non-permissive value. We can also say y equals 0 does not exist. And so because of that, we will have a horizontal asymptote at y equals 0. Because x equals 0 is a non-permissive value, that gives us a vertical asymptote. at the line x equals 0. Right, so we can draw our horizontal asymptote in there as well. That comes from the fact that y can never equal 0. And we can start to graph this or put points on our graph. When x is 10, y will be 1/10. So it's very close to 0, but still positive. When x is 5, y will equal 1/5. When x is 2, y equals 1/2. When x is 1, y equals 1. When x equals 1/2, y is 2. And when x equals 1/4, y is 4. So this gives us one arm or one branch of the graph. And the further it goes in either direction, the closer it gets to the asymptote. So that's one arm or one branch of that graph. We got that from values of x that were positive. They approached 0, but they were all positive. So now we can do the same thing when the values of x are negative. Now we're going to approach 0 from the left side, meaning we might start with something like -10, and then -5, and then -2, -1, -1/2, and -1/4. So when x equals -10, remember y is 1 over x. That'll be -1/10, -1/5, -1/2, -1, -2, and -4. And so this is the other arm, the other branch of the graph, or something like that. If we want to state the domain of this graph, I'll use set notation. All values of x except that x cannot equal 0, but all other real values belong to the domain. The range is the same except the variable is y. All values, all real values of y except 0 are part of the range. Right, and the non-permissive value here is x equals 0. As x gets closer and closer to 0, the graph either approaches positive infinity or negative infinity, depending on which side of the y-axis you're at. Right, so we're going to be looking at some transformations of this rational function. So this would be our base graph that we always start with. And so for this next one, y equals 6 over x. So y equals 6 over x is the same thing as 6 times 1 over x, which means we have an a value of 6. Remember, that causes a vertical stretch. A vertical stretch, that must be about the x-axis. By a factor of 6. All that's really going to do is just make the y values get larger faster. That's all it's going to do. Okay? But we could still, if we want, come up with a table of values for this. Once again, 6 is still a non-permissive value. I'm sorry, not 6, 0 is still a non-permissive value. Let's write it up here. X equals 0 is a non-permissive value And so we're going to have a vertical asymptote at x equals 0. So we can put that in there. And once again, y can never equal 0. A rational function only equals 0 when the numerator equals 0. But again, the numerator is a constant here. So the line y equals 0 is also an asymptote. No matter what number you put in for x, you'll never get 0 as an answer. So like we did before, I can use some values. Let's go -2, -1, 0, 1, and 2. We kind of know what the graph's going to look like. This is just going to give us some points that we can put on our graph. When x is -2, 6 divided by -2 is -3. When x is -1, 6 divided by -1 is -6. I put 0 in there, but we know that x can't equal 0. It's a non-permissive value. It doesn't exist. When x is 1, 6 over 1 is 6. 6 divided by 2 is 3. So again, we know what this graph looks like. This just gives us a couple points that we can put on there. The point -2, -3 is on there, as well as -1, -6. So that's going to be down here somewhere. So that's this arm of the graph, this branch. Looks something like that. On the other side, I'll have the point 1, 6, which is right there, and the point 2, 3. If I wanted to, I could also put the point 3, 2, because 6 divided by 3 is 2. So again, this gives us another arm or branch of that graph. And that's what it looks like. The domain and range will not change here. The domain, all values of x such that x cannot equal 0, but otherwise all other real numbers. Okay. So looking at this next one, this is a transformation of y equals 6 over x, or we can say it's a transformation of y equals 1 over x. So if we say from y equals 1 over x, we've got, again, our a value of 6, which will cause a vertical stretch. About, again, the x-axis. By a factor of 6. And on the bottom, x is replaced with x minus 2, so that is our h value. Remember, whatever happens to the x happens to the x minus h. In this case, it's in the denominator. And also remember that the value of h is always the opposite of what it appears to be, because the general form is x minus h. So our value of h is positive 2, which means it's going to shift 2 to the right. And then we will have a k value of -3, so it's going to shift 3 down. So this is going to change our asymptotes. Because it goes 2 to the right, our vertical asymptote will be at x equals 2. Because it goes 3 down, our horizontal asymptote will be at y equals -3. Again, we can, if we want, get some points for this graph, and I'm going to choose some specific values of x so that they work out nicely. For example, when x is 0, on the bottom here, 0 take away 2 is negative 2. So you'll have 6 divided by negative 2, which is negative 3. Take away 3 is negative 6. So that's 1 point on this graph. 0 comma negative 6 is right there. Another point that works out nicely would be, say, negative 1, because negative 1 take away 2 is negative 3. 6 divided by negative 3 is negative 2. And negative 2 take away 3 is negative 5. So negative 1, negative 5 is on this graph. Another point that would work would be, if we wanted, we could go negative 4, because negative 4 take away 2 is negative 6. 6 divided by negative 6 is negative 1. Take away 3 is negative 4. So negative 4, negative 4. So that gives us 3 points for this branch of the graph. Looks something like that. And on the other side, I could let x equal positive 3, because 3 take away 2 is 1. 6 divided by 1 is 6. 6 take away 3 is 3. So the point 3 comma 3 is on this graph. So that's that point right there. I could let x equal 4. 4 minus 2 is 2. 6 divided by 2 is 3. And 3 take away 3 is 0. So that is actually the x-intercept. And I could let x also equal 5. That'll work out nicely, because 5 take away 2 is 3. 6 divided by 3 is 2. And 2 minus 3 is negative 1. So 5 comma negative 1 is right there. So that gives us a few points on the other branch, the other arm of the graph. Our vertical asymptote is at x equals 2, and our horizontal asymptote is at y equal negative 3. So our domain would be all values of x such that x cannot equal positive 2. All real numbers except positive 2 work. And there's the range. All real values of y except for negative 3. Okay? So again, this would be a transformation of y equals 1 over x, where we have an a value of 4, which is a vertical stretch, about the x-axis, by a factor of 4. We have a h value of negative 1, but whatever happens to the x happens to the x minus h. In this case, it's in the denominator, which means the graph is going to shift one left. And then we have a k value of positive 5, cause the graph to shift 5 up. Because the graph goes 1 to the left, our vertical asymptote will be at x equals -1. And because it goes up 5, our horizontal asymptote will be at y equals positive 5. Okay, so we can label these. This is at x equals -1 and at y equals positive 5. To get some points on this graph, some points that work out nice. I can let x equal 0 because on the bottom 0 plus 1 is 1. 4 divided by 1 is 4, plus 5 is 9. So that's that point. I can let x equal 1. 1 plus 1 is 2. 4 divided by 2 is 2, plus 5 is 7. So the point 1 comma 7, that point there. And I can let x equal 3 because 3 plus 1 is 4. 4 divided by 4 is 1. 1 plus 5 is 6. So the point 3 comma 6 is also on the graph. So this gives us 3 points on that arm of the graph. To the left of -1, -2 will work nicely because -2 plus 1 is -1. 4 divided by -1 is -4. Plus 5 is 1. So -2 comma 1. I can let x equal -3. That'll work because -3 plus 1 is -2. 4 divided by -2 is -2. Plus 5 is 3. So -3 comma 3 is right there. And if I let x equal -5, -5 plus 1 is -4. 4 divided by -4 is -1. Plus 5 is positive 4. So -5 comma 4 right there. So this gives us points for the other arm or branch of this graph. Our domain, all values of x except x cannot equal -1. All real values of x except for -1. And our range would all be all real values of y except y cannot equal positive 5. Okay, so here's a new one, a little bit different. We can see, though, that x cannot equal 2. It's just in a different format, a slightly different format. Okay. So we can see here, because we have a non-permissive value at x equals 2, that's where our vertical asymptote will be. Let's look at this graph on our calculator though, because the equation is in a different format than what we're used to seeing here. So there is a horizontal asymptote, but because the equation is in a different format, it's not quite so obvious where that horizontal asymptote is. So if we put 4x minus 5 in brackets to keep the numerator together, then do the same thing with the denominator. And I'll go zoom 6 to set my windows to their standard settings. The calculator doesn't actually draw asymptotes, but you can see that there is an asymptote there at x equals 2. But you can also see the horizontal asymptote is somewhere above the x-axis. Okay, if we go into our trace mode, and let's say we let x equal negative 5, our y value, or I guess I put in positive 5, and that's okay. Our y value is also positive 5. What if I let x equal positive 10? There's my y value, 4.375. What if I let x equal positive 20? Oops, I got to change my windows. So let's go here to window. Let's put our x max at, let's say, 60. And I'll change my scale to 10. So now I'll graph it, and I'll trace and let, there it went to x equals 25, y is 4.13. What if I let x equal 40? Y is 4.08. What if I let x equal 50? Y is, and you can see what's happening, the y value is getting closer and closer to 4. But it's always higher than 4. That was at 50. 55, closer to 4, but still above it. 60, closer to 4, but still above it. And if I did it on the other side of my asymptote, my other side, so I would choose values of x less than 2 and keep getting smaller and smaller, you would see the same thing, that the graph would approach a value of 4. So that is the horizontal asymptote. A horizontal asymptote is at 4. Now here's a way you can get that, and this always works. When you have a rational function and the degree of the top and bottom are the same, which in this case they are, it's both x to the power 1 on top and bottom. To get the horizontal asymptote, you simply just have to divide the coefficients of those x terms. Again, the degree of top and bottom is the same. In this case, they're both power 1. So when that happens, to get your horizontal asymptote, you divide the coefficients of those terms from the highest power. So y equals 4 over 1, or y equals 4, is the horizontal asymptote. So if you can remember that, then that saves a bit of time for sure. But you can always graph them like we did, and you'd be able to determine where that horizontal asymptote is. Right, so y equals 4 is our horizontal asymptote. And so now in this case, to draw an accurate sketch, we would do like we did before. We would just generate some points. And in this case, it doesn't really matter what values of x we choose, except x can't be 2. That's where our vertical asymptote is. So let's use a couple points to the right of positive 2. For example, we can let x equal 3, x equal 4, and x equal 5. And we can just sub those into the equation. And maybe, because we've already got the graph, maybe we can use our trace mode. Let x equal 3, y equals 7. Let x equal 4, y equals 5.5. And let x equal 5, y equals 5. So I've got the point 3 comma 7, which is approximately there, 4 comma 5.5, which is approximately there, and 5 comma 5. So this gives us one arm or one branch of the graph. And now I'll choose values to the left of 2. So I might choose 1, I might choose 0, and I might choose -1. So again, you can take these values and plug them into the equation, or you can use the graph. 1, 1, 0, 2.5, and -1, 3. So 1, 1, 0, 2.5, and -1, 3. So this gives us points on the other arm or branch. Right, and our domain, all real numbers except for +2. And our range will be all real numbers except for +4. So in this case, we'll have a non-permissive value at x equals 4. So that's our vertical asymptote. Again, the degree of the top and bottom are the same, both x to the 1. So our horizontal asymptote is at y equals 2 over 1, or 2. You divide the coefficients of the x terms, the highest power terms. So there's our horizontal asymptote. So unless the graph is reflected, unless that happens, these graphs will always have our branches in the top right quadrant and the bottom left quadrant. Always. But to confirm that, I mean, you could just do what we have been doing. If we choose values of x to be 5, let's say 6 and 7, plug that into the equation. So 2 times 5 plus 2 in brackets, divided by, on the bottom, just 5 minus 4, which is going to be 1, obviously. That gives us a y value of 12. When x is 6, we get positive 7. And when x is 7, we get 5 1/3. So I have the point 5, 12. I have the point 6, 7, and 7, 5 1/3. So this gives us points on the one arm or branch. And then on the other side, to the left of 4, I might go 3, I might go 2, I might go 1. So first when x is 3, negative 8. When x is 2, get negative 3. And when x is 1. Negative 1 and a third. So negative 3, comma negative 8. Sorry, that's not negative 3, it's positive 3. Positive 2, comma negative 3. And positive 1, comma negative 1 and 1/3. So this graph has a both x and y intercept, which it does ask us to find. We've identified our asymptotes. We can write their equation. This one is y equals 2 and x equals 4. Remember that your intercepts, your x-intercept is where y equals 0. And remember that a rational function equals 0 when the top equals 0. So it's where 2x plus 2 equals 0. That would be where 2x equals negative 2 and x equals negative 1. So our x-intercept is at negative 1, comma 0. Our y-intercept is where x equals 0. So it'll be found again by letting x equal 0 in the equation. So 2 times 0 is 0 plus 2. 0 take away 4 is negative 4. So our y-intercept is at negative a half, the point 0, comma negative a half. All right. So this rational function, we've got 1 over x squared. We're asked to graph each pair and compare the characteristics of the graphs. So they're all being compared to y equals f at x, which is 1 over x squared. So let's just see what that one looks like on our calculator. Again, 0 is a non-permissive value for x, so you're going to have a vertical asymptote at x equals 0, which is the y-axis. But let's see what this graph looks like. 1 divided by x squared. Both arms are above the x-axis. And if you think about it, y can never be 0 because no matter what you put in for x, whether it's positive or negative, you're going to square it. So a negative value of x squared will make it positive. And obviously a positive value of x squared will also be positive. You're always going to have 1 over a positive number, which is always going to be positive. So that's why the graph of 1 over x squared looks the way it does. Both of the arms are above the x-axis. If you want, you could grab a couple points real quickly. For example, when x is negative 1, negative 1 squared is 1. 1 over 1 is 1, so it goes to the point negative 1, comma, positive 1. When x is negative 2, negative 2 squared is positive 4. You're going to have 1 over a quarter, or 1 over 4, I should say, which is a quarter. And when x is negative a half, negative a half all squared is positive 1/4. 1 over a quarter is 4. Again, the x-axis is an asymptote because 0 is a non-permissive value. And the y-axis is also an asymptote because y can never equal 0. A rational function only equals 0 when the top is 0, and the top is a constant. The top is a constant, it's positive 1. So that's why we have our asymptotes there. And the right side of the graph looks the same. It'll go through the point 1, comma 1. It'll go through the point 1/2, comma 4. And it'll go through the point 2, comma a quarter. All right. So what about g at x? Well, g at x is a transformation of f at x. You've got the a value of 3 on top, so that's going to cause a vertical stretch by a factor of 3. But you've also got the denominator, which can be factored. That is a perfect square trinomial. If you factor that, you're going to get x minus 5, or x minus 5 all squared. This is a transformation of f at x with a vertical stretch by a factor of 3 and a shift of 5 units right. That x minus 5 tells us that our h value is 5. Remember, whatever happens to x also happens to x minus h. The two things that are affecting x is that it's a denominator and it's squared. Well, the x minus 5 is also a denominator and it's also all squared. So if we talk about comparing the two graphs, for g at x compared to f at x, you've got an a value of 3 and an h value of 5. So comparing g at x to f at x, we have an a value of 3, which again causes a vertical stretch about the x-axis by a factor of 3, and we have an h value of 5, which is going to cause it to shift 5 to the right. And we did this before. We used a table of values to generate our new points. So I had the point -2, comma, -1/4, or +1/4, I should say. I had the point -1, comma 1, and I had the point 1/2, comma 4. So this is from y equals x squared. Okay. This was from y equals x squared. I also had the point +2, 1/4, +1, comma 1, and +0.5, comma 4. Again, these are the points on y equals x squared, which is f at x. So then for g at x, both of these transformations are going to change. Actually, that's not true. The first one will change the y. You have a vertical stretch by a factor of 3. The second one will affect the x. It's going to go 5 units to the right. So you're going to add 5 onto all the x values. So we can start by doing that. Adding 5 to all the x values. And then multiplying all the y values by 3. could have, but I'm going to get my actual points so that I can graph them. So multiplying all the y values by 3. So I've got the point 3 comma 3/4, and I guess I can put my asymptotes on here as well. Let me just change the color. Something different. So here we have a non-permissive value of x equals 5. That's our non-permissive value. But the x-axis is still an asymptote because y cannot equal 0. And I've got the points 3 comma 3/4. So 3 comma 3/4, approximately there. 4 comma 3, approximately there. 4.5 comma 12, which is way up here somewhere. And on the right side, I've got 7 comma 3/4. I've got 6 comma 3. And I've got 5.5 comma 12. Again, way up here somewhere. So there's that graph. Now, for h at x, I'm going to rearrange the terms a little bit to look like this. That negative sign in front of the rational part can go on the 1, which again we're comparing to y equals 1 over x squared. So we've got a value of -1, so this is for h at x. So let's write this over here, or down below, I guess. We have an a value of -1, which is going to reflect the graph over the x-axis. X is replaced with x plus 4, which means we have an h value of -4, which is going to shift the graph 4 left. And we have a k value of +6, which means it's going to shift up 6. Okay, so that goes on the second graph. So let's draw we're comparing it to y equals 1 over x squared, which we've seen what it looks like. For h at x, we have a non-permissive value at x equals -4. So that will be our vertical asymptote. So again, we'll change the color here. And once again, y cannot equal 0 because the top numerator is a constant. So it'll never equal 0 because the numerator can never equal. Actually, that's not true. Yeah, it can't equal +6 because the rational part can't ever equal 0. So there's no way that the whole thing can equal 6. The only way h at x can equal 6 is if this first part is 0. And it can't equal 0 because the top is a constant. So my horizontal asymptote is at y equals 6. Because the rational part can never equal 0, so the whole thing cannot equal 6. The other way of looking at it is that +6 on the end is going to shift the whole thing up 6 units. So instead of having your horizontal asymptote on the x-axis, the line y equals 0, it'll be shifting up 6 units to y equals 6. Okay, so let's get our points for h at x. And we're going to be coming from f, right? We're coming from f. So the ones that are going to affect our x values are only the h component of -4. We got to go 4 to the left. So from f, we're going to subtract 4 from all the x values. Subtracting 4 from all the x values. And then for the y values, we're going to multiply by -1 and add 6. So multiply 1/4 by -1 will become -1/4. Add 6 will be 5 3/4. 1 times -1 is -1, plus 6 is 5. 4 times -1 is -4, plus 6 is 2. And the y values haven't changed from what's above here, so it'll be the same, 5 3/4, +5, and +2. So -6, 5 3/4, -5, comma 5, -4.5, comma 2. You see, because the graph reflected over the x-axis, this one's going downwards instead of upwards on both sides. I've got -2, comma 5 3/4. I've got -3, comma 5. And -3.5, comma 2. hang on a second. I got -2, 5 3/4. Yeah. I got these couple points in the wrong spot on my graph. That should be -2, 5 3/4. -3, 5. No, I had it right. No, I don't have it right. I got these ones messed up. So let's fix them. When x is -2 up here, -2 plus 4 is +2. Squared is 4. We're going to have -1/4 plus 6, which is 5 3/4. So that was right. When x was -3, -3 plus 4 is 1. Squared is 1. -1/1 is -1. Plus 6 is 5. And -3.5 plus 4 is 1/2. Squared is 1/4. -1/1 is -4. Plus 6 is 2. That's what I had, right? Okay, must have been looking wrong. -3.5. Oh yeah, this is what I did wrong. I've got -3.5, 2. -3.5, 2 is right there. I just have my points in the wrong spot. -3, 5, which is right there, and -2, 5 3/4. So that's what that graph looks like. I think I was counting from the wrong spot. And again, the reason it goes downwards is because the graph reflected over the x-axis. And that's why it goes downwards. Okay, we're going to stop there. We should be able to do on page 450. (442) to 444. Questions 1 through 4. I will post these on Google Classroom so that you can check your work. So yeah, the questions aren't in the book, so you will have to use your textbook for these. But I will post the solutions on Google Classroom so you can check your work, okay? So once everyone has written that last unit exam, then we can go through it. And we'll do that hopefully on Wednesday is the hope. So that I can give you guys your review assignment for those that want to do the rewrite. And then we can schedule that for sometime after Easter. But at least you'll have the opportunity to work on that during Easter. Yes? We already did that one. We already did that one, I think, didn't we? You guys already had the chance to rewrite that. I'm pretty sure. I'm sorry? Okay. All right, then we'll have to find some time to do that then. I thought we had done that, but no, it doesn't look like we did. So, right, I remember I was waiting for Ethan and he wrote it now. So, we will find some time to do that. Okay?
Maybe you went on vacation again.
Yes. Yes. Yeah.
Why would you make exit or why? Because you're
Because the only way a rational function will equal zero is if the top equals zero. To get y to be zero, it has to be zero divided by something. That's the only way. The bottom can't be zero because that's undefined. That's a different scenario. The only way a rational function can be zero is if the top can be zero. So if you had 1 over x, well, that you can't make that equal to zero either, right? Because 1 can never equal zero. Okay, so the only way a rational function equals zero is if the top equals zero. So that's why we let the top equal zero. Okay? Yes.
It's just only a few instructions I got given. It's just a lot of English, God knows social, so much to memorize. Bio, it's basically the same thing. I did a the same way like before. Next one's not next. Slightly better. Yeah. I just like yes. I thought there was nobody goes there other than you want to make enough money to do that. Yeah, they're like the. Do you remember like? Yeah, I remember food.
Remember they really chill. Remember Foot
Not one
Locker?
bucket?
Oh my god, I think it's Foot Locker than that. Yeah. And I'm not.
Because they don't have enough money to sustain
The thing is that everyone's taking work. I don't have to work.
the.
They need something.
It's an unlucky spot.
Yeah,
Because
and
even,
I
because the thing is that expensive.
yeah.
I guess no one's gonna walk into a store and be like, oh wow, $120. Wow, $150.
That's even like
See, that's the thing. You go to the belt.
I see like over the brownies.
Obviously, but being profit, we're gonna have to sell them at high price, right? And that makes a lot of sense. If all of the product is high price.
Yeah, I think we're going to make this.
Yeah, oh my God.
I just sell around them.
It's robbed.
Yes, you know? Cause you're like, oh, it's just $2. Like, $3. Check out $148.
Yeah.
And then let's start by It used to be like an hour. And I was like, I will hunt him down. And worse than the Americans. You know, like, how do you pull this stuff out of me? I feel like I'm so I feel like I'm being like
Yeah. I like the easy, it's just.
Pre-calculus, I like that's 12, we're gonna bring it back.
You think it's actually that Are you sure?
When I get
I'm pretty sure she does.